All right, we are done with circular motion. Sorry, Jaden, I just want to check with you what your teachers are doing now. Gravitation, finally moving on, right, from circular motion, right? But which part of gravitation are you on? What was the last thing you heard from them? Okay, so not orbit yet lah. Hello, Jeremy, put your bag somewhere else, can? Sorry. Okay, so GMM over R, that means it's just starting on gravitation only. Okay, so haven't moved on to other things yet, not orbit yet. Okay, good. Right, that's fine. But we are going on to SHM now. I'm just doing the same pace I'm doing. When I review my last year's recordings, right, this is about the same time I'm doing this topic for. So it's plus minus 1 week, right? It's pretty much the same. Okay, right. So I believe that this pace is the correct pace, right? Even though like my 2 hours, right, my 2 hours with you guys, my 1 hour 45 minutes with you guys is like really just me downloading content onto you, right? Okay, right, and you have to do the practice outside of class. Right, so we're going to do SHM now, right? We're going to do this thing called simple harmonic motion, right? They're called oscillations, called simple harmonic motion, right? So we're going to this chapter. Give you an overview of this set of notes. So this set of notes is done in this way. There's 4.1 in the first part. This is 4.1. You see 4.1? 4.1 here, phase difference, angular frequency, defining equation. This is all 4.1, 4.1, 4.1, 4.1. Right, then you go on to this part here all the way. You flip your notes and see for yourself. Then you start seeing this syllabus here. I break up the syllabus here. This is 4.1. All right, but everything that we've done above, right, all the notes above this page is all summary here lah, all summarized here. Then 4.2 is here. There's a 4.2 here. Now 4.2, right, my notes for 4.2 is this syllabus guide from the IB side and the blank space there and the blank page at the back here. That's my notes for 4.2. Okay. All right, because we're gonna do a lot of our own drawings here. All right, we're gonna do a lot of our own drawings here. All right, then 9.1 is at the back. 9.1 is at the back. So I must tell you this, okay? 4.1 and 9.1 are taught together for HLs, right? I think this is the usual case for. There is no value in teaching it separately, right? Because it's really very closely related. So we have to learn how to use these equations also. So I think some of you have seen the equations before already, right? Right? Maybe the teacher just did this, briefly show you, and then close it, and then say, okay, let's move on to the next topic already. Right? Now I'm not gonna do that. I'm gonna explain everything to you. Okay? So this is 9.1. So 4.1 and 9.1 are together. Right? So the order of cylinders for 4 and 9, right, can be very confusing because I think IB made a mess of it. Honestly speaking, I think IB made a mess of it. 4.3 is split into two parts. 4.4 is also split into two parts, and the two parts are not related to each other. It's very strange. Okay? The 4.1 is related to the second part of 4.3, second part of 4.4, and 4.5. Right? Whereas first part of 4.3 and first part of 4.4 is also totally different things. It's very annoying. Okay? Right? So, well, I mean, you just follow my pace, you follow my schedule. Okay, can. All right? So then in chapter 9.1, you will learn energy in SHM. So we start off first by this. What is an oscillation? Oh, it's not written here, but what is an oscillation? So it's not written. So a lot of things are not written in my notes because, these set of notes here, right? I realize that if I print out everything for you, you will not remember everything at all. So I'm making you all memorize this. I'm making you all write this down. So you all got paper, no? You all got paper, no? Extra paper, right? Extra paper. Right? Please write this down. You sleep enough or not?
No.
I keep asking you to sleep more, right? The night before. What time do you sleep last night? That's okay, what time do you wake up this morning? Huh? I thought you got training. Then you sleep for 11 hours. You sleep for 11 hours, and you still sleepy. Yeah, wake up. That's not an accident. That's not an accident. No. Take and take and share. Take and share. Goodness. Take and share. All right. So if you're feeling sleepy, right? I've got some stuff. I'm just short of using an electric prod only. Okay. And what's an oscillation? An oscillation is a periodic to and fro motion. Right? An oscillation is a periodic to and fro motion. Okay? Periodic to and fro motion. Periodic oscillation is a periodic to and fro motion. Jialat. You are damn jialat.
Double S. 1S.
1S lah, I think. Well, you test me, is it?
Yes.
Right. One S lah. Right. Oscillations. Oscillating. Jialat. This one. How should I do this? Oscillations.
Periodic to and fro.
Oscillations. It's not working. Okay. Oscillations. And then, right. Don't hello me. So strange. Okay, hang on. Oscillations. Okay. Right. Periodic to and fro motion. Right. Yeah. About an equilibrium point. Sorry. Periodic to and fro motion about an equilibrium point. Forgot to add that in. Periodic to and fro motion about an equilibrium point. About an equilibrium point. Periodic to and fro motion about an equilibrium point. Okay. So I am gonna just like break it to you immediately. There's mechanical oscillations and then there's non-mechanical ones. The only non-mechanical ones that you learn is in alternating current, but that's like next year stuff. Don't worry. Okay. So we're always doing mechanical. Mechanical means an object, right? So mechanical oscillations. So I'll tell you this, okay, guys. You see this, You let it swing, right? This is an oscillation. Okay, this is an oscillation, but this is not SHM. Okay, SHM, right? There's some specific conditions, but this is not SHM, even though it's a pendulum like that. Let me show you what's SHM, okay? For pendulum. Pendulum, SHM is like this. This is SHM. This is simple harmonic motion, right? But when it's swinging like that, no, it's not. Right? There are some reasons why. Okay, there are some reasons why. I'll go through the reasons later on, but I just want you to remember this in your head, okay? So SHM is just like that. Okay, this is SHM. Right? Where the displacement is almost horizontal. If your displacement is like that, is it horizontal? No, right? The displacement is what? Is an arc, right? Is an arc. If it's an arc, right, then it's not very SHM already, right? The approximation to SHM is very bad. Okay? In fact, this is more like circular motion because it's an arc. Right? So I want you to understand this, okay? Circular motion is not SHM. Circular motion might be a type of oscillation, but it's not SHM. Can you write this down? Circular motion is not SHM. Right? Circular motion is not SHM. Right? SHM SHM M. Stupid. Okay, SHM, right? So for SHM, right, simple harmonic motion, right? It's called simple harmonic motion. Simple harmonic motion, right? Yeah. So that's a short form for SHM. I don't have to write anymore. I can just dictate it my way through everything. All right. There are very specific conditions to fulfill SHM. Okay. All right. There's very specific conditions to fulfill SHM. I'll go through the conditions later. Right. But there you go. Okay. So take note that there's very specific conditions. So if you don't fulfill the conditions, you are not SHM. You may be oscillating, but it's not SHM. So oscillations is a to and fro motion, right? But SHM is a very specific subset of oscillations, right, where you fulfill the conditions. And we only study SHM. We only study SHM. Yes, we study circular motion, yes, but we don't consider that as oscillation at all, right? So, and then we study SHM for oscillations. Okay? Okay? That means you must always fulfill this set of conditions. Right. So, we start off first by understanding a few terms lah. All right, we understand a few terms. Amplitude. What's the definition of amplitude? It's up there in my notes. In my notes, flip open the notes. Right, it's in my notes. Definition of amplitude. Maximum displacement from equilibrium. Right? So if you are okay, so I just want you to understand like there's only a few systems that we do in physics, right? For oscillations, right? So I tell you what, why don't you use the space at the bottom here, we draw out all the systems that you ever need to care about. Okay, first we draw the pendulum, right? So we draw the pendulum like this. Okay, this is your pendulum. This pendulum has a to and fro motion, right? You have a to and fro motion. The displacement is, right, from the equilibrium position, that's x, right? So displacement is always from the equilibrium position. So what's the equilibrium position of a pendulum? Right down the middle, right? Okay, right down the middle, right? But I want you all to learn the language a bit, okay, right? I want you all to learn the language a bit. So I'm gonna ask you this, okay? When is the speed of the pendulum the greatest? When is the velocity the highest? Okay, so at equilibrium, right? Okay, so I want you to change that phrase from now, right? Because when you say something is at equilibrium, right, you got a feeling that you're trying to say that the object is in equilibrium, right? Which is not, because it's moving, right? It's moving, right? So you might be mistaken that it's like a, by saying at equilibrium, you might be thinking that it's at rest, but it's not at rest, okay? So I want you to say this, okay? The speed is greatest when it passes through its equilibrium. When it passes through the equilibrium position, all right? Passes by, okay? So the speed is greatest when it's passing through the equilibrium, all right? So passing through the equilibrium. So just take note of that, okay? Right? This is not the conditions, this is not the requirements for SHM. I'm just trying to teach you all the language only, right? So like what he was saying just now, he said at equilibrium. So I'm trying to correct that because in case you get like very used to it, right? Then you make a mistake later on. Okay, anyway, I said I want to go through all the systems. This is the first system that you need to care about. The next system you need to care about is horizontal spring mass, right? There will be a spring and there will be a mass, and the object will be subjected to oscillating back and forth like that, right? Back and forth like this, right? This is a spring mass system, okay? A spring mass system. So it'll go from here to here to here, right? So it's at its most compressed now, then it will go back and forth like this, right? Back and forth like this, all right? Equilibrium position is right in the middle here like this. So when it comes to rest, it will rest in equilibrium.
What's X?
Yeah? X is displacement, right? X is displacement, okay? X is displacement. But if it's a maximum displacement, then it's called x naught. You can call this x naught if you want. If you're marking out the amplitude, then you can call it x naught. X naught stands for amplitude, right? X naught stands for amplitude. Okay on this, Ken? So this is the second system. Now there'll be more details later on. I'm just trying to introduce you all the systems first. Okay. Then you have this system, which is a vertical spring mass system. A vertical spring mass system. So your vertical spring mass system is kind of like this, right? You have a spring. Where's my spring? Oh, here. Where's my weights? Oh, here. So it will look something like that, okay? So I give you this thing here like this. Right, so something like this. Vertical spring mass system. So you have a spring, a mass, right, and then it goes up and down like this. You know what I mean? These oscillations. Okay? This SHM we can consider this directly to be SHM. So all of these things here, they do SHM, right? But I want you to just take a look at this vertical spring mass system. Of course, like I said again, I'll go through more details later on. But for now, I'll just introduce you to the system. Right now, what is it at? Equilibrium, How do you get it to oscillate? You push it down, or you can even lift it up. If you want, right, you can also lift it up and let go. Okay, you understand this? But here's the trick, okay? You see, right, this is the equilibrium position. If I were to pull it down by 10 cm, right, then that's the amplitude. That's 10 cm. The amplitude is 10 cm. So what that means is that it will oscillate between 10 cm below the equilibrium and 10 cm above the equilibrium. So it will go like that. Understand what I mean? Okay. So this is oscillation here like this. So vertical spring mass system. Okay. But the thing that might confuse you, right? The thing that might confuse you is this one here, right? How can a slinky can a slinky do horizontal spring motion? Can a slinky like this one do horizontal spring motion? Cannot, right? because it can't be compressed. Right? It cannot be compressed. So for the horizontal spring mass system, I want you to imagine it's kind of like this kind of springs, right? Where you can extend, right? You can extend a bit and you can compress a bit. It's like your G2 pen spring. You know your Pilot G2, right? The pen spring inside. Same thing, right? So the idea is that you can extend. So the object will be just oscillating back and forth like this. Okay? You see this? Right? It'll be oscillating back and forth like that. Okay? Can yeah. So these are the three major systems, to be honest. These are the three major systems. Right? The three major systems. But I said there's actually a couple more. Right? So I'm just going to go through the other two. The other two are particles. The other two are particles. Particles on a transverse wave. So you see, right, when you have a wave, okay, if let's say your wave is traveling this way, right? If this is a water wave, if let's say you have a wave traveling this way, if this is a water wave, what is your particle doing? Particle is doing what? Up and down, transverse wave, right? It's oscillating up and down like this, right? So I want you to learn this right here, right now. The particle is doing SHM. Yeah, the particle is performing SHM. Right? Pretty much like this one here, the vertical spring mass system, right? Right, up and down like this, right? So draw this in, right? Draw this in, right? I think that's what your teacher was trying to say. SHM is related to one of the things later on, right? The one of the things later on is actually 4.2. Yeah, right. How the particles move. It's a SHM movement. Okay, you remember the equation for waves because we're going to do waves later on, right? V equals F lambda. Remember the equation V equals F lambda, right? V equals to F lambda is for the wave, not the particle. V equals to F lambda is for the wave, not the particle. The particle got its own set of equations. I mean, what does V equals F lambda mean? Is V constant?
Yeah.
Yes, it is, right? The wave speed is constant, right? Look at this particle. Is his speed constant?
No.
No, what's he doing? He's speeding up, slowing down, speeding up, slowing down, speeding up, slowing down, right? He's actually changing his speed all the time. So V equals F lambda cannot be used on a particle. Can? Now, I want you to guess what's the last system that you need to figure out. Eh? Light. No. Yeah, sound wave. Yeah. Light, right? Polarization, right? That one, right? Got nothing to do with this. SHM got nothing to do with that one at all. Right? It's a transverse wave, yes, but we can't see the particles. Yeah. So in any case, yes, sound wave, right? What does the sound wave do? Yeah, the sound wave, right, oscillates left and right, in a series of forming a series of what? Yeah, refractions and compressions, right? The nonsense, right? You remember all this nonsense, right? Yeah, nonsense. Right? Then you got your refractions and compressions. So while your wave travels this way, right, your particles are actually oscillating back and forth, right? And then so what are the particles doing? The particles are doing SHM also. They're also oscillating back and forth like that, like going back and forth like this. You got it? Can? Yeah, learn how to draw a longitudinal wave. This is how it looks like. Strangely enough, right? Compression and refractions. Good. Very good. Okay? There we go. Right. So these are the few major systems that you will be using. Alright. Okay. So an object moving in a circle, is it SHM? No, it's not. So it's not part of these systems, right? So you'll be focusing on these five things, right? For the whole part of SHMs. Right? They'll be asking you to calculate the speed, the acceleration, the displacement, all these kind of things. They're just asking you to calculate stuff. Right? So you don't really have to worry that much, right? If in doubt at any point in time, if you're not sure, if you try to visualize it, always think of the pendulum. Yeah, always think of the pendulum. Like if I ask you, because for the pendulum is very simple. At the amplitude, what's the speed? At the amplitude, what's the speed of the pendulum? Zero. You all can tell me that instinctively, right? So that's great already. So and all of them are the same. At the amplitude, all of them their speed is zero, right? The displacement is maximum. Okay, good. So now back to my notes again. Sorry about this, right? Now we go through the things properly, right? Amplitude is what? The maximum displacement. Read the word maximum displacement, right? From equilibrium position. So I can give you, let's say I give you a sound wave, let's say I give you a sound wave and I recorded it on a microphone and the sound wave looks like this. Right? Then I ask you, so what's the amplitude of the sound wave? I want you to indicate the amplitude of the sound wave in this picture. How would you indicate it? Yeah, from the line all the way to the bottom here, right? This would be the amplitude. Right? This would be the amplitude. Fair or not? Okay? Why? Why is that the amplitude?
It's the maximum displacement from the equilibrium verification.
Yeah, exactly, right? Because according to the definition, I want you all to find the maximum displacement from equilibrium position, right? This is it, right? It's literal, like, you know, whatever they read down there, maximum displacement from equilibrium position, that's exactly what they want. Okay? Period, what's period? Period is time taken for one complete oscillation. So amplitude, please write down the symbol is x naught. Period is capital T. Don't go and write small t. Don't go and write small t. Period is big T. So what's small t? Time, right? Small t is just time. Frequency is f. The relationship between frequency and period is f equals to 1 over t, right? And then you have this thing called angular frequency. Angular frequency, the symbol is omega. Right? Yeah, like what? Yeah, so the thing is this, where else do you see omega not too long ago? When was that? Circular motion. But that omega was defined as what? Now, I mean, the equation is that, but the words, the omega in circular motion was called angular velocity, angular speed. In this chapter, you cannot call it angular speed. You cannot call it angular velocity. You can only call it angular frequency. Okay? All right, angular frequency. Because, right, I'll explain why, but the equation is still exactly the same. 2 pi over t and 2 pi f. Can you write this down, please? 2 pi over t and 2 pi f. All right, I need you to pay very close attention to this one. This is very important in case you made a mistake. Right? This angular frequency does not refer to an actual angle. Does not refer to an actual angle. Okay? All right? Angular velocity in circular motion, yes. Angular velocity was what? Was the angle that the object covered, right? In a certain amount of time, right? It was 360 degrees, right? That's circular motion. So that's angular velocity. But in this chapter, angular frequency is not a real angle. So I must tell you this because you might think that, hey, does it mean the pendulum's angle is the angular velocity? That's not at all, zero. What's the angle here? At most is what? 5 degrees, 10 degrees. No, for SHM, the small one, right? 5 degree, 10 degree only. It is not this angle, okay? Right? And the trick is this, okay, also. Okay, one more thing about the pendulum. Okay, so in case nobody, oh, the spring just sprung. Wait, where did my spring go? Yeah, sorry. The spring just sprang away. Okay. Okay, so if nobody told you this, I'm going to tell you this now. You see this pendulum? Okay, you see the pendulum here? The length is constant. I'm going to displace it by 5 degrees. I let go of it. Okay? The period is whatever period it is, right? You take a timer, you go and time the period, right? I take this pendulum, I raise it to 8 degrees. Not too much, but 8 degrees. I let it go. It's the same period as the 5 degrees. Increasing the angular displacement will not increase the period. The period will be exactly the same still. Right? And the reason is because the length controls the period. So if the length is not any different, right? Even if you raise it by 5 or 7 or 8 or 10 degrees, right? The period is exactly the same. Yes, it is traveling a longer distance by traveling faster. If it's traveling a shorter distance, it's traveling slower. So it's still the same. Okay? Alright. So angular frequency is not referring to this angle. So what is angular frequency about? In fact, what are the other systems? What are the other oscillating systems that you just learned? What's the other few? spring mass system, vertical spring mass system. What else? Particle moving up and down, particle moving side to side, right? What does angle have to do with any of them? Right? There's no angles in these, right? So the most common mistake that students make for angular frequency is to think that it's something to do with angle. It's not, right? But here's the trick. You complete one oscillation, it's 2 pi radians. One oscillation is equal to 2 pi radians. Okay? One oscillation is 2 pi radians. 2 pi radians, of phase. Right? We're going to learn this new word later, phase. Okay, 2 pi radians of phase. Okay, if you complete half an oscillation, how much phase is that? Half an oscillation, pi radians. In degrees? 180 degrees. So I want you to understand this. Oscillation, right, is a sine curve or a cosine curve. Okay, right? It's a sine curve or cosine curve. So if you see, right, this is a sine curve, and this one here is a cosine curve. All right, it just means one wave. One oscillation is one wave, right? One wave is 2 pi radians. So when we talk about angular frequency, right, in this chapter, omega is basically 2 pi. That means one oscillation divided by what?
T.
What t is this? Small t or big T? Big T, right? There you go. 2 pi radians is one oscillation divided by one period, right? Is your angular frequency. That means how many oscillations covered per unit time. Can? Right? Yeah. So after all the years of teaching, right, I realized that this thing, right, they don't explain in school. That's why a lot of students get damn confused later on. They'll be like, what's this pi? Why is there pi or something like that, right? So oscillations is related to these two graphs. Furthermore, I'll point out one more thing also. If you look at a pendulum, right? If you look at a pendulum, if you want to swing a pendulum, why do I keep wrapping this up and keep unwrapping it? Okay, if you want to swing this pendulum, how would you swing it? You have to displace it first, right? That means you have to start from amplitude, right? Then you let go, right? Okay, now. So some people start to think that because of that, right? Because of what I just did, then all oscillations should only start from here, right? Because you should only start from amplitude, then you can get a cosine curve, right? Right. So my point is this: these two graphs are the same thing, right? It's not about how you start the oscillation; it's about where you start observing the oscillation. Can I get you to understand this? What's the difference between these two graphs? The difference between these two is the difference where you start observing the oscillation, not where the oscillation starts from. I mean, obviously, how is a pendulum supposed to start from equilibrium without like that? It can't start, right, from here. But then I'm telling you that these two graphs, right, you can use for oscillations, right? So I must remind you that these two graphs depends on what? Depends on when you start observation of the oscillation. Can you just write that comment down? Right, it depends on which graph to use, depends on when you start observing the oscillation. So the idea is this, guys, the pendulum was already oscillating, right? The pendulum was always oscillating like this. Right, like that. It was already oscillating, right? So you didn't know how it started. You didn't know whether it started on the right side or started on the left side. You didn't know that. Okay, it was already oscillating. The trick is to figure out when do you want to start observing it. You can start observing it at the amplitude, right? Let's say you take a video and then you pause it when it's like this. Okay, can. Or you can start observing it like this. You take a video and you pause the video when it's here, but it's actually moving past the equilibrium, right? Okay. So if you start observing from the equilibrium, then the graph looks like this. If you start observing an amplitude, then it starts looking at this. But guess what? What happens if you observe starting from equilibrium but moving in opposite direction? You could also get the negative graphs of it. You could also get this one here and this one here. You could also get right. There's actually 4 combinations in total. Right? There are 4 combinations in total. Right? One oscillation, whatever it is still 2 pi. Right? And that will never change. Right? Because by mathematics definition, that's what one oscillation means. 2 pi radians. So yeah. Okay, can so I settle the small terminologies for you all. Right? These are all the small terminologies. Can? Right, but there's one thing that I haven't gone through yet. This word that I just introduced not too long ago. Phase. Phase, right? Phase. Phase is basically defined as stage of oscillation. Phase is which stage are you at, right? Phase, right? What's the phase of oscillation? What's the stage of oscillation? So just write down phase equals to stage of oscillation. Right? Phase equals to stage of oscillation. Yeah? Okay? There we go. And this thing confuses the heck out of everyone. I don't know why also. Everyone's like very like concerned about phase difference. They're always very concerned about this thing called phase difference. Okay? Right. Phase difference means what? Difference in there you go, right? Good, right? Excellent. Stage oscillation, right? But if you want to find the difference, right? Can I do this? Can I give you one pendulum and I ask you this? What's the phase difference of this pendulum? Right? You'll be like, what? If you want to find the difference of anything, it's always a difference of something versus another thing, right? If I give you one pendulum only, do you think it's fair for me to ask you, what's the phase difference of this pendulum? You'll be like, oh, what are you asking? What kind of strange question is it? Right? So I have to give you another pendulum. I have to give you another pendulum to compare to. Okay? So let's say I have two pendulums, two pendulums, right? One of them is longer, all right, one of them is longer, one of them is shorter, right? So for exaggeration, right? Okay, right now both of them are at their amplitudes. Okay, right now both of them are at the amplitudes. Even though the short one is the short one, right, and the long one is the long one, both of them are at their respective amplitudes. What is the phase difference now? The phase difference is 0, right? Despite them having two different lengths. Because phase difference is based on what? Stage of oscillation. It is not comparing the time, it's not comparing the length of the string. I'm not comparing the periods or anything like that. I'm comparing the stage of oscillation. Both of them are at their amplitude stage now. So what's the phase difference between the two? 0. Right? I'm not comparing any time at all. I'm just asking you, so what's the phase difference? Okay? Alright, can. Alright. So let's say, how about this? One pendulum on this side, the other pendulum on the other side, like this. Right? One is on a negative amplitude, one is on a positive amplitude. What's the phase difference? In terms of oscillations, how many? Okay, in terms of oscillations, how many oscillations is this? Like, how many oscillations are they away from each other? Half an oscillation, half an oscillation. Good, right? The phase difference is half of oscillations. Is what, like what Jeremy said was pi what? What's the unit? Pi radians. Pi radians. Okay, pi radians. All right, you can say it's 180 degrees. So in general, phase difference, which is expressed as phi, right? The symbol phi is equals to pi radians. Can you write this down? Right. The next set of my notes is phase difference anyway, so you can see that down there. It says phase difference here. Okay. So it's expressed as pi radians. So we just show you that between A and E, comparing the positions of A and E, right? The phase difference is phi equals to pi radians. Phi equals to pi radians. Yeah, okay with this? You good on this? Can Now, the symbol phi is not used officially in IB, right? That's just me teaching you the actual thing, right? So, yeah. Can So phase difference is just a difference in stage of oscillation. Ian, are you okay there? What time do you sleep last night? Quite early also. But you had math earlier on, so we share. Okay. So do you need any other sustenance? You can pass that back to over there. You wanna take one more and pass it back? Yeah. Okay. I must tell you also, right? Later on, right, in topic 4 point something, they will ask you phase difference of waves. Guys, they'll ask you phase difference of waves. Ask you phase difference of waves. Can Alright. So, but then that one later lah. Don't worry, okay? That one later on. But let me show you all. Let me show you all. Okay, let's say I have two waves like that. One wave. Why my this thing jump? Don't jump then. Wait. Okay, let's say I have two waves. Uh, what's the phase difference between these two waves? Yeah, good. You all can tell it's zero phase difference. Like if you have no phase difference, right? Then you are in phase. In phase. In sync lah, in sync the boy band.
No.
You mean you don't know the boy band? Jialat. Not the right generation, right? Backstreet Boys, you all know Backstreet Boys? Yeah. You all don't know in sync, what the hell? Okay. Not that.
One Direction.
One Direction. What happened to them? They completely disappeared.
You know one of the members had 3 nipples.
Okay, I didn't need to know that. Why? Why? Okay, but this shows you that the two waves are in phase. Basically, you have two objects that are oscillating, right, in the same sequence, right, because they have the same stage of oscillation. Do you see how the amplitudes match? Amplitude match amplitude, right? Then zero match zero, amplitude match amplitude, zero match zero. So they are in phase, they are in sync. Even if one started before the other, let me show you this. Even if one started and the other one only started one later, right? This is still considered as in phase. Do you see this? This is still considered as in phase. This is still considered as in phase. Even though one started and then the second one only started second, like, one wave later, right? This is still considered in phase. So I need you all to learn this. Phase difference, right? Jeremy, write this down. No, I want you to write the next thing down. If your phase difference is 2 pi radians, that means one wavelength, one oscillation, right? If your phase difference is one oscillation or / one wavelength, okay? That's the same as saying no phase difference at all.
What's one os?
One oscillation.
Oh.
One S only, ma. You really want me to write down everything, One oscillation. Oh, okay. Don't lose, don't lose. Win, okay? Always win. Don't lose. Okay, there we go. So phi is equal to 2 pi radians, or you can consider it as one oscillation, or you can consider it as one wavelength. But we're not doing waves yet, right? We're doing oscillations for now, right? So there's no wavelength, has nothing to do with it, right? Okay? Yeah, wavelength has nothing to do with it. Not now lah, right? So it's kind of like I just shade it off a bit, right? So because we're doing SHM, we're going to be doing a lot of SHM from like the next 1 hour, right? What, you want to crash already? Just 1 hour only. What? Oh, you know correction tape. Who has correction tape? I thought you have.
No.
Run already.
Wow.
What you want? What? It's just no. Cannot. Okay. All right. So there we go.
Axis. What's the axis stand for?
Oh, that's a good question. Okay, usually the the y-axis is always going to be amplitude, displacement. The y-axis is always displacement, right? Displacement. And the x-axis is usually time, sometimes distance.
Distance.
Yeah, distance. Yeah, don't worry about that later on. Okay, how does out of phase look like? How does like out of phase? If I tell you something is out of phase, right? Out of phase, then you would imagine that the curve, right, will be like something like this. This out of phase, right? But I must tell you this, okay? This is what is this? This is completely out of phase. This is like, okay, hang on. If you're in phase, right, there's only one way to be in phase. It's like that Colgate drawings that you all drew inside your paper just now. That doesn't look like Colgate. Toothpaste, right? I show the rest of them. And then this one, it looks like toothpaste, right? The blue and the white and the red. Yeah, toothpaste. Yeah, but it is, right? So there's only one way to be in phase, right? There's only one way to be in phase, and you have to be like perfectly in phase, right? To be out of phase, right? You just don't have to be in phase, right? Okay, wait, don't draw the next one, Next one, don't need to draw. Let me show you this. Wait, is this in phase?
No.
This is not in phase, right? Is this completely out of phase? This is not completely out of phase. This is what we call slightly out of phase. This is like slightly out of phase. So if you want to be completely out of phase, then you have to do it like that, like completely antagonistic like that.
Okay.
Then this is called out of phase, right? That means when it's positive, this one is confirmed negative. When it's positive, then the other one is negative like that, right? This is completely out of phase. What's the phase difference for this? What's the phase difference of this? Yeah, pi radians. This would be pi radians, right? Pi radians, or rather what? How many oscillations? Yeah, 180 degrees, good. 180 degrees, half oscillation, right? Half oscillation, or based on wavelength? Half wavelength, right? It's half wavelength, half lambda. Okay, can try to remember this for the whole of 4 and 9. I know these things that I'm telling you, right, actually will help you understand 4 and 9, like all the way down to 4 and 9, right? So some students that like in the past, like last year like this, right? Some students joined me like halfway through, like 4 and 9. They finally decided that they got enough of not knowing what 4 and 9 is all about. Then they join, right? Then in the end, they have no idea what these are. They get damn lost, right? So you have to know this, right, for 4 and 9. Okay, so what Jeremy is drawing is what are you doing? The red one is slightly out of phase, okay, and the green one is completely out of phase, right? 90 degrees. Okay, yeah. In fact, I think you drew your red one to be so nice that it actually looks like it's 90 degrees out of phase, right? You see that it looks like it's 90 degrees out of phase, right? So anyway, I just show the rest of you. Wait, you drew finish this one already? Finish already? Okay. Let me show you how does 90 degree out of phase look like. 90 degree out of phase, right, is this. Where it's positive, right, you start from 0. Then you draw the graph. Then this will be 90 degrees out of phase. Right, 90 degrees out of phase. Right, so where I start 90 degrees later, I start 1/4 of an oscillation later, right? 90 degrees 1/4, right? Okay or not?
So which one will be the one is like the one is like the mirror image is completely out.
Yes, that's right. This is partially out of phase. This one is partially out of phase. All right, we'll come back to this again for waves, but I think you already, that's why maybe it's a good thing that you learn now. Okay, now I would just want to add on a little bit to this drawing here. I want you all to be able to see this. Oh, Jeremy, you added in also, good. All right, so I'll wait for everyone to be able to look up first. Okay, you see where it starts from, right? You see the blue one starts at 0, the red one starts at 0 also, but like a quarter of a wave later, right? Not. But I want you to learn how to connect it back to time equals to 0 like this. You kind of like you just complete the curve here. You complete the last part here. This one. Darlene, do you see this one? This part here? Like it started off like this at first. Then I added that portion there like this. I added this portion here like that. Okay? Right? Can you tell me what's the functions that you're looking at? The blue one is what function? Sine. The red one? Technically, negative cosine, right? So I want you to remember right here, right now, phase difference between sine and cosine, right, is always 90 degrees. Right? Phase difference between sine and cosine. Phase difference of sine versus cosine, okay, is always 90 degrees, right? So maybe you just learn this right here, right now, lah. Always 90 degrees. In terms of radians, pi over 2 radians, okay? 1/4 oscillation, 1/4 of a wave. All right? Now, this will come in later. So we'll come back again, but I'll just remind you again later on, right? Landon, you finish? Still drawing? Okay, slowly. Get it right, Okay, good. Yeah, excellent. Right, then you write down this statement. Phase difference between sine and cosine. Okay. Now, a sine wave is a sine wave, a cosine wave is a cosine wave. I think you all understand this, but I want you all to know this also. When we use the word sinusoidal, when we use the word sinusoidal, right? The word sinusoidal is a blanket term for both sine and cosine. Sinus, yeah, literally sinus, then you soil the sinusoidal. Yeah, lol, not lol, not sinusoidal. Sinusoidal. Oh, sorry, the. Oh, I thought you were asking about the last letter. Yeah, sinusoidal. Okay, sinusoidal. Okay, yeah. Right, that's just a blanket term. Okay, can I go back to my notes? Go back to my notes, Okay, good. So angular frequency, we done this, so we know this already. So this one here done, right? The amount of this basically the number of oscillations per unit time, right? In radians, okay? In radians, right? This is the amount of angular angle covered in terms of oscillations. The defining equation for SHM is A is equals to negative omega square x, right? Okay, this technically is not in 4.1. This technically is 9.1. You can't find this equation on the topic 4 data booklet. Yeah, you can't find this, right? But don't need lah. All you need to care is this. This equation helps you to do what? This equation helps you to calculate the acceleration of a SHM object, right? So what do you need if you want to calculate the acceleration? What do you need? You need the angular frequency, which means that you need a period, or you just need the frequency. And what do you need here? X is what? Displacement. Okay, x is displacement. Okay. So let's say I tell you that I have a pendulum. Let's say I have a pendulum, and I tell you that the displacement right now is 5 cm. Okay, and I tell you the angular frequency is 20 radians per second. Right, 20 radians per second. No lah, maybe not 20. 20 sounds very big. 2 radians per second. Then I ask you, so what's the acceleration right here? What's the acceleration right here, right now? No. No. Omega square x, right? Omega square x. So negative 2 squared times 5 equals to Negative 20 cm per second squared, right? That will be the acceleration. That's it. That's all there is to this equation, right? So it's like you given one thing, you find the other thing. That's pretty much it. Yeah. Yes. That's what the purpose of this equation is for. Alright? But that's the purpose lah. That's the purpose. What's the significance of this equation? Right? I mean, you know the purpose, but now the question is what's the significance? Okay? The significance is, oh sorry, actually, right, guys, this, if I take positive to be the right side, technically the displacement here is -5. So I'm gonna put -5 here. So what is the acceleration then? Supposed to be positive 20, right? Supposed to be positive 20. Okay. Right, yeah. So this is quite kind of important. Right? So this displacement is not distance, right? Displacement. Displacement means that you need to be concerned about the positive and the negative side, right? Okay. Alright. You okay with this? Okay. What this means is that if your displacement is pointing to the left like that, and you calculate the acceleration, you realize the acceleration is pointing to the right like this. Maybe it's amplitude, maybe it's not. I don't know yet. But I do know whatever it is that right now, right now, right, the object is swinging backwards, right? It's swinging backwards. But since it's swinging backwards, the acceleration is pointing forwards, right? So let's talk about. So now we know how what the equation is for. Let's talk about the significance of the equation. This equation is what we call the defining equation of SHM. This equation is called the defining equation of SHM. Down here, defining equation of SHM, right? And according to this defining equation, number one, acceleration is directly proportional to the displacement. Directly proportional means what? Directly proportional means that A is directly proportional to X. That's what it means. What that means also is the bigger the displacement, there you go, right? The greater the acceleration. And in what kind of relationship? Directly proportional means what? Means it's a straight line passing through origin. Right? Because I'm gonna ask you this, okay? I mean, what happens if you have a graph that looks like this, guys? If let's say I ask you plot A versus X, right, and the graph looks like this, is this directly proportional? Is this directly proportional?
No.
No, this is not directly proportional, right? Why? I mean, it's exponential, it could be quadratic, it could be something like, right? But we don't know, right? So whatever it is, it's just not directly proportional. But why is it not directly proportional? Because it's not a straight line. Yeah, because it's not a straight line. It's passing through origin, but it's not a straight line. You need to be a straight line, right, for directly proportional. You understand this? Yeah. Okay. So if I tell you this, hey, I have an object that does this. I have an object that does this thing. Is it SHM?
No.
Is this SHM? No. Why not? Because it's not directly proportional, right? It's a very thing. Yeah, it's a very logic thing. Like if yes means yes, if no means no, right? So if it's not directly proportional, it's not SHM. It could be oscillation, yeah, for all I care, it could be some sort of oscillation, but it's not SHM. It's just not SHM. Okay? So what's the other definition of this SHM? Right? So firstly, it must be directly proportional to the displacement. Secondly, it must be opposite direction. How do you know it's opposite direction? Yeah, but what's the thing in the equation that tells you? Yeah, the negative sign. The negative sign is the reason why we know that it's opposite in direction. It has to be opposite in direction. You okay with this? Can Can Right? So that's the significance of this equation. What this means is this all SHM. You see, remember the 5 systems I gave you? Pendulum, horizontal spring mass, vertical spring mass, transverse particle, longitudinal particle, all of them, all 5 of them must agree or must obey this law, then they can be considered as SHM. If it doesn't, not SHM. Okay, so my question to you now is this. Why is circular motion not SHM? I mean, the value of the acceleration is always constant, yes. The acceleration is not constant. What, where?
Same direction as the force. Then it's like it's not opposite to displacement.
No, he's absolutely right. That's the one answer that I require to get to answer this. Right? For circular motion, the acceleration is pointing towards the center of the circle, but the displacement is where? The displacement is perpendicular. It's not opposite in direction, right? It's perpendicular, right, to the direction of acceleration. Therefore, by this, circular motion is not SHM. That's it. Hey, write this down somewhere. Right? Displacement is perpendicular to the acceleration, not opposite. Therefore, it's not SHM because SHM requires to be opposite direction. We good? Can? Alright, good. Okay. Yeah. So circular motion is not SHM simply because SHM has to follow these two criteria, like I said right just now. So your pendulum, your horizontal spring mass, your vertical spring mass, your longitudinal transverse particle all must agree to this defining equation, right? And therefore they'll be considered as SHM. Okay? Okay, good.
Okay.
So now my question to you is, based on this, why is this pendulum not considered to be SHM, but yet this one is? I started the lesson off today, right, by giving you a large angle, and when I give you a large angle, it doesn't really do SHM, it does more of circular motion. It's more like a circular motion, right? And if this is circular motion, where's the acceleration actually pointing towards? Yeah, the acceleration is actually pointing towards here, but then the displacement is where? And the worst thing is that the displacement is not even a straight line, it's a curve, right? So this doesn't behave like SHM, right? So case in point, if you ever done this pendulum experiment in school, right? You remember the pendulum experiment where they ask you to take the period of 20 oscillations? If you did this, right, it's completely wrong. If your pendulum was swinging like this in the lab, right, this is completely wrong, you know. Like, I don't know whether some of your teachers, if your teachers were kind enough to point out to you, right, they would have pointed out to you that this is the wrong way of oscillating a pendulum. In that 20 oscillation pendulum experiment, you're supposed to oscillate it with small angle only, like that. Yeah, you're supposed to do this only. Okay? Now, why though? Because when it is small angle approximation, or when it's small angle pendulum, right? Small angle pendulum, the acceleration is pointing this way, which is almost opposite to the displacement, which is pointing that way. This makes it SHM. Okay? But why though? Why is the acceleration like pointing this way now? Okay? Because when you look at when you zoom in on the pendulum, right? The pendulum has tension and the pendulum has mg. Okay? when you resolve the tension has two portions, right? Two components, right? If let's say this is theta, and then this is t sine theta, and this is t cosine theta. Okay? Okay so far? So then we'll take this as the this the acceleration, causes acceleration
Okay.
of SHM. Okay, some teachers will go into the very deep end of this and start deriving the entire equation from you starting from here. Don't bother. Don't bother. I'm just going to tell you this, okay? You just have to remember this. Pendulum, right, no matter what, is an approximation to SHM. Pendulum, even though it's the most common SHM that we always use, technically speaking, is an approximation only. Okay, it's an approximation. Why is it an approximation? If you look at it microscopically, this path is still an arc. This path is still an arc. Do you see this? This path is still an arc. But we approximate it to what? You see this path here is actually an arc, right? But we approximate it to what?
Straight.
Yeah, we approximate it to a horizontal line. We approximate it to a directly horizontal line like this. Okay? I don't know whether you remember this from Sec 4. When do you approximate chord length, sorry, arc length to be equal to chord length? Arc length to be approximately equals to arc length, when chord length, sorry, arc length approximately equals to chord length. When does it happen? Small angle approximation. Do you remember that? Small angle approximation. Eh, didn't you do that in Sec 4? Eh?
No.
No man? Eh, they took it out already ah? Eh, but it's only for I mean you will do it in IB lah, but oh, I didn't know they took it out from Sec 4. Oh, Sec 4 I still remember my A math, I still have to do small angle approximation. Sine theta approximates to theta. Anyway, none of your business, don't worry about it. Okay? Right? Just write this down. SHM is an pendulum is an approximation for SHM. Pendulum is an approximation for SHM. Let's stuck my eye. Eh, put down. No. I'll give you a break in a while. Hang on, huh? Okay, but this is only one of the systems, right? Let's look at all the other systems, Can we look at all the other systems? Can I? Let's look at the horizontal spring mass system. Horizontal spring mass system. In fact, the most legit system, right, is actually the horizontal spring mass system. But it is almost impossible to do that in real life. Because in real life, right, the object's weight will weigh it down. Then the spring wouldn't be horizontal. The spring will like be a bit koyak like that. Yeah. So that's the irony of it. So even though the horizontal spring mass system approximates is the best representation of SHM, okay, it is not really feasible in real life. Okay, let me show you this. Let's say that's the equilibrium position, right? And this is the most negative amplitude. Most negative amplitude. This is minus x. Can minus x. Yo, minus x. What's happening to the spring? Good. Compressed. Compressed, right? You see the spring? It's compressed. Okay, compressed, huh? Which means what's the direction of force acting on the mass? Yeah, so the force is pointing this way, right? So there's a force pointing this way, right? So where's the acceleration of the mass? Pointing to the right. So the acceleration is pointing this way. Opposite direction? Opposite direction. Yeah, force on the spring. So this is actually equal to kx. Spring, right? Spring force, right? Kx. Eh? Then now you know. Now you remember. What's k? Spring constant. Spring constant. Spring constant. Right? Spelled with k. Spring constant. Spring constant. Okay? Spring constant. But the acceleration is towards this direction, right? I mean, in a way, right, you can think of it as kx equals to ma lah. Kx equals ma, correct or not? Right? Kx equals ma, yeah. Okay. I mean, what happens if this mass continues to move further back? If let's say if it continue to move further back, then what happens to the force? Force will be increased, right? Because like more compression, then greater force, right? Then if the force is greater, what will happen to the acceleration? Even greater lah, right? So one thing to take note of, acceleration is not constant, so you cannot use any kinematics here, okay? Right? Acceleration is not constant here, right? Okay, how about when the mass is like stretched out all the way, like all the way out here like this, right? On the other side like this, right? The displacement is what? The displacement is positive, right? Positive displacement, but the force becomes what? So instead of compression is what?
Rarefaction.
Huh? Hello, that's for sound lah. This is a spring, right? So instead of compressing the spring, what's happening to the spring? The spring is extended, right? The spring is extended, right? Okay, extended. If it's extended, then what this tension trying to pull it back, right? So the force acting on the mass will be pulling it this way, lah, right? You understand this? Right? But you see, right? So the spring works this way. If you compress it by x, let's say you compress it by 2 cm, then when it oscillates, right? When it extends, it will extend by how much? 2 cm. So it's like 2 cm compression, 2 cm extension. So the amount of force is the same, right?
Yes.
Hey, hello. Primary school, is it? I'm primary school. Teacher is him, not me. Dude. Acceleration is pointing. Okay? So one of the ways that some teachers like to teach this is to tell students that always remember that acceleration is always pointing towards equilibrium. They like to say that, right? Always remember acceleration pointing towards equilibrium. Right? Acceleration is always pointing towards equilibrium. Displacement could be pointing towards or away from, right? Oh no, sorry. Yeah, displacement could be positive or negative, right? But acceleration is always pointing towards, right? Equilibrium.
Yeah.
Right or not? Okay? Good. Right? So that's why they like to call this force, right? They like to call it the restoring force. The restoring force.
Wow.
Idiot. Write it down, interesting.
Wait, acceleration.
No. This force is called the restoring force. And it causes the object to accelerate towards the equilibrium. Right? Accelerate towards the equilibrium. Wow, like you draw already, you put one big Ghostbuster sign over it. Okay? Right? It's called the restoring force, right? It's trying to restore it. But you know, the thing is this, even for vertical spring mass, right? You see, you try to restore it, right? So it's trying, like, let's say you pull it down, it's trying to restore it. But then because of the energy, right? The stored energy, Landon, right? It will go past the equilibrium and go back down again. You know what I mean? Right? So it's like, it tries to restore, yes. But once it reaches the equilibrium, it gets a bit too fast and it just goes towards the back. Right? Then after that, got a lot of EPE, right? Elastic potential energy, then it gets pushed out. Then as it pushed out again towards equilibrium too fast, it will stretch outwards like this. Yeah, just keep on going back and forth like that. Can? Right. In all your oscillations, we don't consider loss of energy. We do not consider loss of energy. Do you understand this? Right? If there's a loss of energy, the effect is called damping. Can? Damping, which means that you can do that for your IA. So I'm going to start talking about IA already, because one thing more often than not, right? Topic 4 and 9 gets the most IA topics on. I don't know why also. Like if you try to do IA topics from any other chapters, right? The teachers will always like, not good lah. They'll tell you kinematics not very good, dynamics not very good, or something like that. I get a lot of like over the years I get a lot of IA topics from 4 and 9. That means waves, that means polarization, you've got like oscillations, you got damped oscillations, that sort of thing. Like I get a lot of this everywhere. You got this thing called resonance also, but it's not in your syllabus. It's not in your syllabus. Yes, this thing called resonance is not in syllabus. Yeah, it's not in syllabus. That's why you don't know. Yes, okay, good. Yes, but in physics, I mean the idea of resonance is the same in chem and physics. Ah, you're doing resonance in cam already, ah? Then when ozone absorb the UV rays by resonance, ah? Oh, wow, okay, okay. Then how come it looks like you never hear before? Oh, HL cam?
Yeah.
Did I know that?
Yeah.
I knew that.
Yeah.
Did I not advise you against it?
No.
Walao eh, jialat bro.
I'm too
You,
different, bro.
walao eh, you better.
Feature kind of easy.
Honey boy, what?
My first
No, I mean, I agree with you. I really like chem and bio because to me, those two subjects are very easy.
bio that L, bro.
Bio easy ah.
Oh, bio is
Bio easy lah. Yeah, you all cannot like that lah.
bio
You
don't
all.
even need go class. You just need
Bio.
one textbook and you
Yeah, just memorize the whole thing. Oh, yeah, correct. Oh. He's exactly right. Don't even need to go class one.
very easy. Ah.
Okay. Do you need a break? Do you need to take a toilet break? Okay, go toilet break. Go. I'm gonna take a toilet break. I eat my chocolate. You want chocolate?
Yes.
Mm.
Okay.
Pass. What stupid game is that?
Oh, it's called ball.
Is it the what? There's another game. Was it 2460 or 1240?
2048.
Yeah, 2048.
I never played that game.
Oh my god, are you serious?
I reached 16,000.
Wow.
Say 2048. Like 4 times. It must be tough, man.
Hey, go toilet lah. I thought you all want to go toilet.
No, my brain's very numb. I actually burst my brain.
Okay, wait. Eat chocolate. Okay. Numb already or not? Social media also numb your brain also lah, dude. I know it's really using social media. Alright, let's do this. So vertical spring mass system, right? The vertical spring mass system is gonna be the same except, right? I wanna just point out to you, so if you have a vertical spring mass system, right, and it oscillates between the top and above, right, between the bottom and the top of this equilibrium line. You see how this object goes up and above, below and above like this, right? So it goes up and down like this, right? So this is a vertical spring mass system. This one is not so straightforward, right? In fact, vertical spring mass system is actually one of the hardest things to do in oscillations, right? Which is very strange, right? Horizontal spring mass system, okay, suddenly vertical spring mass system totally not okay. Yeah, it's not totally not okay because of this. When the spring stretches to the most maximum position, right? You see this most maximum position. Can you tell me like T1 compared to mg? Yeah, T1 is greater than mg, right? T1 is greater than mg. Then you got like, wow, you got the two equations. So T1 minus mg will be equals to the ma, right? With the acceleration of the object. Jason, what are you smiling at? What's tickling you? It's okay. Sometimes you know, I also think of things, right, and then I laugh to myself also. People think I'm a bit crazy sometimes. Okay. But then once this object goes up, right? Once this object goes up, the tension is completely different. In fact, the tension is like much smaller, right? Then the mg is still like that. So at the top, mg minus T2 equals to ma. Right, so that's the problem with vertical spring mass system. Vertical spring mass system, right? There are two forces to consider. So that's why I say, right, the horizontal spring mass system is actually the easiest thing to understand, right? And then all the others are actually quite hard. Okay, so there you go, right? Yeah. Okay lah. I'm already going through a lot of details already. In fact, we are covering a bit of 9.1 stuff already. Yeah, we are really covering a bit of 9.1 stuff already. Like you know, yeah. It's just that I have to bring this up again. So you just keep this drawing somewhere important, somewhere, and then make sure you bring it in the next lesson,
Yes.
Okay. All right. So yeah. Okay. The you know, if you consider this to be positive displacement, positive x, then this one here will be negative x, right? So your displacement will be based on, like, you know, which direction, up or down, right? You could choose up as positive, you could choose down as negative also. So it's like, you know, it really depends on where you want. Okay, but I'll tell you, don't have to worry, right? Later on, then we will settle this. Okay. So these are all the systems and how how does the acceleration, right? So actually the acceleration for this one is pointing downwards, the acceleration for this one is pointing upwards. Sorry, I just want to add in these two arrows. The acceleration here is pointing downwards, right? Because mg is more than T2, right? Mg more than T2, so downwards is the prevalent direction. And this one here is T1 is bigger than mg, so upwards is the prevalent direction, right? Okay. Can I? Right, keep it there, Jeremy. Just keep it there. Just give me another half an hour more. Right. Yeah. Okay, then yeah, of course you got your longitudinal particles, and you got your this horizontal particles, like, you know, transverse particles and all that, right? Okay, do you still need this up here, darling? No? You okay already, guys? Okay, I kinda. Right. But you know what? Do I need to go through it? So your particle go down and go up. Yeah. Although you might not know where the force is coming from. Yeah, you see, right? If let's say I give you a string, right? If I give you a string, right, and a string wave like this, right? And I look at this particle here. Let's say there's a string particle here like this. Okay. What's the displacement now? What's the displacement of this particle?
Positive.
Positive. And any other things to take note of? Is the maximum displacement, right?
Yes.
Is at the amplitude, right?
Yes.
The displacement in which direction? Is the displacement is positive, right? This is positive displacement. Where's the acceleration?
Negative.
Yeah, the acceleration will definitely be pointing down, right? So it will start to accelerate towards the equilibrium, right?
Yes.
Right or not? But then the question is, where's the acceleration coming from for this particle?
That's true. the street.
Where is it pointing?
Up. Indicated.
Not bad lah. It's 10.
The side there.
Okay, so it's actually pointing this way. Yeah, it's pointing sideways like that. Because the particle in the middle is being held on by his friends, right? His friends are like pulling him down, right? Oh yeah, wow, what an analogy, right? Or you could be here, then your friends are pulling you up. Right? So this guy here, the neighbors are like pulling him down, so the resultant force is pointing downwards, so that's why it accelerates downwards like this. Right? Again, I'm just trying to show you how the direction is opposite. That's all. Okay? You okay with this?
Okay.
Okay, Alright, let's go and do the graph first. Let's go and do this nonsensical graph there. Thing here. On this page. Back to my notes, this one here. So you're supposed to draw a graph of acceleration versus displacement based on that equation, the negative omega square x. Right? So you're supposed to plot you're supposed to plot AX graph with the negative, yeah, AX graph. It's on this page. There's a page that gives you this one here. Ask you to plot a graph on AX graph. Oh no, you drew there. Okay, never mind. Just draw on the left side. An AX graph. The graph looks like this. Okay, straight line through the origin down. Right, straight line through the origin down like this. Right, hang on. This is x naught. This is negative x naught. This is a naught. A naught, and this is negative a naught. Okay? Alright, what does this x naught, negative x naught, a naught, negative a naught mean? What's that? Maximums. Correct, good. So the maximum displacement, the maximum negative displacement, the maximum acceleration, and the maximum negative acceleration. What do you notice? When it's negative displacement, what's the acceleration? Positive, right? When it's negative acceleration, then it's positive displacement, right? You get away. See, this line passes through the middle. So your job is to understand this. As the object is oscillating, left, right, left, right, left, right, you are actually going up and down this graph all the time. This graph gives you the limits to it, so it just goes like, this way, up and down, up and down, up and down this way. You get what I mean? Okay, cool. Yes, that's quite cool. What other things do you need to notice about this? What is the acceleration when the object is passing through the equilibrium? Yeah, the acceleration is 0. But what's the velocity?
V naught.
Maximum velocity.
Oh, is it?
Right? Okay, so here's the thing, you listen. As the object goes towards the equilibrium, goes past the equilibrium, the velocity is a maximum. Right? The velocity is a maximum. You understand this? Okay? Right? But the acceleration is? The acceleration is 0. Okay, so let me just illustrate this for you, okay? Okay, zoom into a pendulum. Now the pendulum is going towards the equilibrium here, like this. Okay? Right. Can you describe to me the acceleration at the amplitude? What's the acceleration at the amplitude? Right, maximum acceleration. So I want you all to be able to understand that the acceleration is like that. Now, okay, I'm going to give you some numbers. If let's say this is minus 5 cm, for example, let's say the maximum negative amplitude is minus 5 cm like this, right, as it goes to the left. Okay, this is stage 1, right? Stage 1 is here. Guys, can I ask you this? When the object has moved from 1 to 2, right? Stage 2. Let's talk about stage 2. When the pendulum has moved from stage 1 to stage 2, right? What's the displacement here?
Less than 5.
So what's the displacement? Let's say it's in the midpoint between here and here. So the displacement is negative 2.5, right? Okay, hang on. Wait. I want you all to pay very, very close attention to this. when you move from 1 to 2, right? When you move from 1 to 2, your displacement is based on where? Your reference point is based on where? Displacement. Equilibrium position. So you must understand this, okay? I tell you this, if let's say from 1 to 2, right, the object move, okay, I give you a trick number. Let's say I tell you that the object moves 2 cm. What is the displacement of the position 2? Negative 3. The displacement of position 2 is minus 3 cm. Do you understand this? Yeah, I mean that's the thing that I'm trying to get at to you guys. If the distance moved from position 1 to 2 is 2 cm, the displacement of the object at position 2 is minus 3 cm. Right? Because it's always based from the equilibrium. Yeah. The most common mistakes that students will do is to think that the displacement is 2 cm because I displaced from 1 to 2. That's not it. For oscillations, displacement always reference from where? From equilibrium. So even if I move 2 cm from here to here, right, the displacement of the object in position 2 is negative 3 cm. Are we okay in this? Can I? Alright, negative 3 cm. Listen up, listen up. So I want you to consider this. What is the acceleration at position 2? What is the acceleration at position 2? What's the acceleration at position 2? Well, basically less than the acceleration, the maximum acceleration, right? So can you imagine the acceleration is getting lesser and lesser, but it's still accelerating, which means that it's still getting faster and faster, right? It's still getting faster and faster. Yeah. In fact, can you calculate the acceleration here? Yeah, 3 out of 5, right? The acceleration at position 2. The acceleration at position 2, yeah, is 3 over 5 of the acceleration, the maximum acceleration, 3/5. Right, because I'm just comparing the ratio of the displacements, right? Yeah, there you go. That's it. Yeah. All right. So, yeah. And then the acceleration at position 3? Yeah, it's 0. Right? 0 lah. Acceleration at position 3 is 0. Okay? So, what happens to the pendulum as it swings towards? The displacement is getting less and less negative, right? Not that it's displacing positive, the displacement is getting less and less negative, the acceleration is getting less and less as well, right? And then the acceleration there is 0. What happens to the velocity then? How about the velocity at position 3? Velocity at position 3. Yeah, maximum, so we consider this to be maximum. Yeah, okay with this? Can okay, good. Right, so as long as you can remember this, then I jump on to the next equation already. Yeah, write this down, write this down. Huh? Minus 3 cm.
Okay, I'm done.
You're done. Okay, ready? Let's do the next thing, So what does the defining equation give you? A relationship between what and what? Very good, acceleration and displacement. And you understand what displacement is now, right? Displacement is always based from equilibrium. So even though it's swinging towards the equilibrium, the displacement is still considered to be negative, right? And therefore the acceleration is always pointing forwards like this. Okay? And it's pointing until it becomes, and somehow it decreases until it becomes 0 here, and then the velocity becomes maximum here, right? When it passes through the equilibrium position, right? When it passes through the equilibrium position. Can I close this now? Okay, close this now. Then let's go through the next thing here, right? This table here is just to show you this table here. Is it a Beyblade? Is it or what? Hey, it's always at this time of the lesson, right? The last 15 minutes, right? Just focus. Just give me the last 15 minutes focus. 15 minutes only, 15 minutes. This table here is just to show you like the directions, right? Just a summary of the directions. When the displacement is here, the acceleration is pointing there. When the displacement there, the acceleration is pointing here. Okay, again, that's all. Don't worry about this. Yeah, hang on, hang on. Strange, strange. Wait. What's he doing here?
Hey, that equation looks familiar.
Yeah, it is familiar. What's this equation doing here? Why is it so far away? Okay. Hang on, I should teach it though. I should teach it. Yeah. Sorry, the rearrangement is a bit off. Can you, I don't know, if you all want to just take out this page from the ones that I printed, you take out this page, you pull this page out, and you put it under the defining equation. You pull this page out. 26, you go to page 26. Okay, go to page 26. And then you, for those I don't know, you all can edit the PDF like this. Can ah? Wow, so good. Right, so you just cut this page out. Wait, cut this page out.
Then we'll take out 28.
What's it? Let me see. The one behind, what's that? What's the one behind?
It's energy in SHM.
Okay. Then like that. Then those who have the don't take it out. We just write it down. We just write it down on our own. Okay. All right. So we go back up here. We go back up here. Sorry about the mess. All right. I don't know why this is not fixed.
See the velocity displacement.
Yeah, the velocity displacement equation. Hang on. Why is my notes like that? Hey, it's jumbled up. I haven't fixed it yet. Sorry. Okay. Just insert a page here for those who want. Insert a page after page 9 if you want. Right? Or page after page. After page 10. After page 10. Right? Insert a page after page 10. Right? And then we're going to do this thing. Okay? So there is an equation that helps you to find the velocity with respect to the displacement, but you've got to learn how to read this thing. Okay? All right. So I'll break it down for you. Don't worry. V stands for what?
Velocity.
Yeah, lah. Then the W.
Angular momentum.
Yeah, omega angular frequency. X naught.
Rate displacement.
Amplitude. Okay. Amplitude. Then minus amplitude squared minus displacement squared. Okay. So what's the purpose of this equation? This equation helps you to find the velocity at any point. Yeah, at any x. Because x can change, right? X naught can't change. What's x naught again? Yeah, maximum displacement, right? X naught is maximum displacement, is amplitude, right? So this value can't change, but this x can change all the time because, like, as it's displacing, as it's oscillating, the x changes all the time, right? Okay. So that's what this equation does. It just helps you find the velocity for any x that you have. Yeah, that's it. That's all there is. Yeah, yeah, angular velocity. So if let's say I tell you, right, there's a SHM. Okay, I tell you SHM. The period is 2 seconds, right? I just give you a period of 2 seconds. The amplitude is 8 cm, right? Then I ask you what's the find V when x equals to 3 cm. Like I ask you to find the velocity when it's 3 cm. Can you do that?
Yes.
Yeah, very straightforward, I think. Oi,
Oh, okay.
write down this one. This is the question here.
The angular.
You figure it out. You figure it out.
I see.
I see.
I see. Square root 55.
Give me values lah. Don't tell me this kind of thing. You're using cm, so your final answer is cm per second. So 22.3 cm per second. Sorry, 23.3 cm per second. 23.3, okay. 23.3. You don't need lah. Yeah.
That one determine one, right?
Oh no. He's right. It could be plus or minus. What? Why is it plus or minus? Huh? No. You actually can't. This equation can only tell you like this. Let's say something like this, right? If let's say this is the where's the diagram? Here. If let's say this is your amplitude 8 cm, right? Okay. And then I ask you what's the amplitude, what's the speed when it's 3 cm, right? Down here, when the displacement is 3 cm, right? You actually can't tell whether or not this pendulum is still going towards the right side or still is coming back from the left side. It's like it's you can't tell whether or not this pendulum is going towards the right or going towards the left. That's why your answer, yes, you have to leave it as plus minus. They're done. You have to leave it as plus minus. Why? Because you can't tell unless I give you more information. But that also means it's a good thing. It also means that it's symmetrical, which means that when your pendulum is at this displacement, right, the speed is either pointing this way 23 or pointing that way 23.
Yeah. Right.
Okay, so we can't tell. We only know, right? We only know that it's either pointing this way or that way. They
Yes.
listening is one thing, no. You know, super memory, right? Write it down, draw the diagram. Guarantee you cannot remember one. The only way to remember is to draw and write. Even if you draw it one time also not enough. You know those super memory, those kind of like people who can memorize the whole IKEA book one. Have you seen that the advert like a couple of years back? This lady go and memorize the whole IKEA catalog. No, then they like she has some super memory bank thing lah in her head lah. Okay, she has a what is it called, memory vault. Sorry, she has a certain set of skill that helps her memorize things lah. Whether or not it's useful, I don't know. Okay, but it's just a way to memorize things, right? They can ask her this, how many clocks are there in the entire catalog? She can remember. She can count. No?
How many
Clocks. Yeah, in the IKEA catalog.
like customer service.
Then after she can even tell the person who's asking the question which pages to look for the clocks.
Yes.
What's the point? I don't know lah. But I mean, if you can tap into that kind of memory techniques, right, it actually can help you to memorize things. I think that's the most important thing that I wanted to point out to you all. Memorizing things is definitely a very important thing to do, especially if you're taking HL Chem. Yeah, legit, you need to learn how to memorize things. You need to be very good at memory work. No, you know why memorizing is so important? It reduces your mental load. When you're doing questions, right, it reduces your mental load because then you won't have to like, I think like that. Then the whole paper is just I think like that, right? So you memorize things to reduce your mental load. I mean, keep it layman's English. You memorize things to make it easier. Yeah, when you memorize things, right, it becomes easier. Let's say, for example, I ask you to memorize like I don't know, all the sulfite.
Easy, bro.
Right, no problem, right? Sulfite. What is sulfite?
Sulfate.
Oh, you have to memorize all that, right? Bicarbonate, all these kind of things. Oh, okay. So when you memorize it, your life becomes easier. I don't care what people say. I don't care what your teacher say or what kind of nonsense Instagram shit you look at. Right? People say that memorize less, learn more. Right? That's all bullshit. You memorize first. All right? This memorize first. Your national anthem, you memorize first or you understand first? Yeah, you understand. You know what Marikita means even at this age. Then Marikita, the first part of it, you don't know, right? Everyone knows what Majula Singapore is, right? It means for honor Singapore. We know that. But what does you memorize the words first, what? You memorize rhyme. No, but that's the thing. That's the irony of it. When you make things rhyme, you memorize better, and that's the trick to memorizing things.
But the ear exhausting cannot memorize.
Huh?
Ear exhaust. you cannot memorize.
No. I don't care what people say, okay? I don't care what all of them say, right? Memory work is one of the most important skills in life. I'm not done yet. Why are you packing? I'm not done yet. Why are you packing? I mean, we're still on this thing, okay? And the last thing I want to do today, please, go and memorize, go and figure out how to memorize things, right? Don't let anyone tell you don't memorize things, This is just a fallacy, okay? Right? You know why there's so many research on how to memorize things? Like there's an entire branch of neuroscience dedicated to helping students research on how to memorize things. What are the things to memorize? Like, what are the ways to memorize things? And memory work is a very important thing, right? I mean, you remember where you stay, right? You remember which keys open your doors, right? That's called practice. Okay, so if you were to plot that equation into a graph, the graph looks like this. Yeah. Yeah, in neither. So it's like a ellipse. It's more like an ellipse, like this. Yeah. Okay. Huh?
What's this graph?
This graph is the graphical representation of that equation. Yeah. Hang on, let me just draw a bit nicer. Can? Alright, label all your parts here. This is a x naught, this is your v naught, this is your negative v naught, this is your negative x naught. So what do you understand when x is 0?
Maximum velocity.
Maximum velocity. Why is it maximum velocity when x is equals to 0? Right? You sub in 0, right? You sub in 0 here, what will happen?
Last W.
Right? So it becomes v equals to omega x naught. So your maximum speed is when you have zero displacement, but it's omega times x naught. Right? Maximum speed is omega times amplitude. Maximum speed is omega times amplitude. Okay, this equation, right, leads to this graph. This graph helps you find out when is the speed maximum.
Sure.
Yes. Then how you memorize?
Yeah,
You draw to memorize what? Then what's the technique of memorizing just looking at? Eye power.
Actually,
Eye power.
Just remember it like.
yeah, that's confused. That's your brain.
If only you had one. Hey, right lah. Right, finish already or not?
Yes.
Right, finish or not? Write this down, okay? Right. Say that maximum speed when displacement equals to 0.
Yes.
Right? When x equals to 0. And the maximum speed is calculated with the amplitude. So v naught equals to omega times x naught. When is the speed 0?
The amplitude.
At the amplitude. Why? That's when x equals to what?
Max.
X equals to what? X equals to x naught.
Oh.
So it's x naught squared minus x naught squared. What happens? 0 lah.
Oh, okay.
You see that? Then everything else can be found from the equation, right? So it's like if x equals to x naught, right, then v equals to 0, right? Because x naught squared minus x naught squared. We okay so far? Can Okay, good. All right. I think I'll stop here.
Okay, bye-bye.
But I want to remind you, these two graphs, right? The acceleration displacement graph and this velocity displacement graph applies to which systems?
Sure.
SHM systems. So meaning all the movements that I gave you just now, the vertical spring mass, horizontal spring mass, the pendulum, all of them, right? These two graphs apply to all of them. Okay? Can? Alright. Next week I want to continue from this graph. Can someone remind me next week, right? I will be doing loss of energy from this graph. If your object loses energy, how does the graph look like?
Okay.
Right? If object loses energy, how does it look like?
Test. Eh?
Oh yeah, next week got that.
Oh, 126 ah.
Yeah.
Did I give you any papers?
Ah yeah, easy lah.
Hey, those who got tests ah.
Hey, but next week we got no test.
No, you know my chemistry test moved to week 9.
Wait, when's the test? When's the test? This coming Friday. So you got 5 days ah.
Oh, this stuff.
Next week, bro.
Hey, those who got test one ah.
Almost tested. Almost tested.
126, right? Didn't somebody tell me 126? 12? I thought I heard 6 somewhere. Someone said 6, right? Didn't you say 6?
I don't know.
Did. Hey, go and find out, Ken.
Hope you asking